Mathematicians are the most careful thinkers on the planet. I mean that if you want somebody to build a perfect chain of logic link by link with no gaps and no guesses, you go to a mathematician. They start with axioms, they prove theorems, they check every step, and at the end of all that work, they have something no one else in any other field can claim to have. They have certainty. Absolute, bulletproof, unshakable certainty. A mathematical proof, once established, is true forever. It was true before anyone proved it, and it will be true long after everyone who cares about it is dead. Now I want you to hold that thought, because I once walked into a room full of these people, some of the sharpest mathematical minds you could assemble, and I asked them one question. Just one, and not a single person in that room could answer it. The silence was, I must say, very satisfying. But I am getting ahead of myself. Let me start by giving mathematicians their due, because they deserve it. The things they have accomplished are staggering. Take a number like pi, the ratio of the circumference of a circle to its diameter. Simple enough idea, right? You draw a circle. You measure around the outside, you measure the line through the middle, you divide. But the mathematicians showed that pi goes on forever. It never repeats. It never settles into a pattern. It is an irrational number. And they did not show this by measuring circles. They showed it with pure logic, a proof, airtight, done. No one will ever overturn it. No experiment will ever disprove it. Or take the square root of 2. The Pythagoreans, way back in ancient Greece, proved that this number cannot be expressed as a fraction of two whole numbers. The story goes that the fellow who discovered this was thrown off a boat for his trouble because the other Pythagoreans found the results so disturbing. But disturbing or not, the proof stands. It has stood for over 2,000 years. Nobody is going to overturn it next week. And it goes deeper than that. In the 19th century, George Cantor proved that there are different sizes of infinity. Not just one infinity, but a whole hierarchy of them. The set of whole numbers is infinite. The set of real numbers is also infinite. But the second infinity is bigger than the first. Genuinely, provably, irrefutably bigger. That is a mind-bending result. It upset a lot of people at the time. Some mathematicians call it a disease. But Cantor's proof is airtight, and it stands to this day. This is what mathematicians do. They discover truths that are eternal, not probably true, not true within some margin of error, not true until new evidence comes along. True, period, full stop, forever. And they do it using nothing but pure thought. No telescopes, no particle accelerators, no laboratories. Just a pencil, some paper, and a brain. And I have to admit, that is a very impressive thing. We physicists cannot say the same. We have Newton's law of gravitation, which worked beautifully for a couple of centuries, and then Einstein came along and said, well, actually, it is not quite right. We have classical mechanics, which is a gorgeous framework, and then quantum mechanics came along and said, well, actually, at small scales, none of that applies. In physics, every law we write down is provisional. It is our best guess until somebody finds a better one. We live in a state of permanent uncertainty, always one experiment away from having our most cherished ideas overturned. So you can see why some mathematicians look down on us, just a little. They have certainty, we have approximations. They have proofs, we have theories. They deal in truth, we deal in models. From a certain angle, it looks like mathematics is the real foundation of knowledge, and physics is just the messy application of it. And here is where it gets interesting, because a lot of physicists agree with this. A lot of very smart physicists have said essentially that physics is written in the language of mathematics. Galileo said it. He said the book of nature is written in mathematical characters. And if you look at physics, it certainly seems that way. Every law we have is a mathematical equation. Gravity follows an inverse square law. The energy of a photon equals Planck's constant times its frequency. Maxwell's equations tie together electricity and magnetism in 4 beautiful mathematical statements. Take the math away and what is left? Just a bunch of vague descriptions. You cannot do physics without mathematics. So the picture seems clear. Mathematics is the bedrock. Physics borrows from it. Mathematicians discover the pure truths, and then physicists come along and use those truths to describe the messy, imperfect physical world. That is the story, and it sounds very reasonable. It is also completely wrong, and I can show you why. Let me tell you about those mathematicians I was sitting with. This was during one of those interdisciplinary seminars. You know, the kind. People from different departments come together and try to talk to each other. Usually it does not go very well, because mathematicians and physicists speak what sounds like the same language but means very different things. So there I was, and one of the mathematicians was giving a talk, a beautiful talk, I should say, very elegant. He was working through a proof about spaces with n dimensions, not 3 dimensions, not 4, n dimensions, where n could be any number you like, 5, 12, 1,000. It did not matter to him. Now I raised my hand, and I said, "That's very nice, but I only need 3. He smiled the way mathematicians smile at physicists, which is a kind of patient, slightly pitying smile. "Well, Professor Feynman," he said, "the general case includes your special case. Just substitute n equals 3. "I know," I said. "But why do you need the other ones?" "Because the theorem is more general. It applies to any number of dimensions." "Sure," I said, "but which ones are real?" And there it was, the question. Which ones are real? Because here is what the mathematicians never seem to worry about. They can build the most beautiful logical structure you have ever seen, with every step perfect, every deduction flawless, every conclusion airtight, and the whole thing can have absolutely nothing to do with the physical universe. Not one thing. They can prove theorems about 17-dimensional spaces. They can prove theorems about infinite-dimensional spaces. They can prove theorems about spaces that curve in ways that no physical space has ever curved. And every one of those theorems is true, mathematically true, logically true. But true about what? About nothing. About an abstract game played with symbols on paper. And that is not a small distinction, that is the entire ball game. See, there is a difference between truth and relevance. A big difference. I can make up a set of rules right now. I say all bloops are floops, and all floops are droops, therefore all bloops are droops. That is logically true, it is valid reasoning, but it is meaningless. It tells you nothing about the world. Mathematics, at its most abstract, is doing something very much like that. It is exploring the consequences of axioms. And the axioms are chosen not because they describe reality, but because they are interesting, because they lead to elegant theorems, because they appeal to the mathematician's sense of beauty. And beauty is wonderful. I love beauty. I love an elegant proof as much as the next fellow, but nature does not give a damn about your sense of beauty. Nature does what nature does, and it is our job to figure out what that is, not to tell nature what it ought to do. This is the trap that very smart people fall into. They confuse the map for the territory. They get so good at manipulating the map, at drawing exquisite maps with extraordinary detail, that they forget the map is not the place itself. The map of New York is not New York, and the mathematical description of a falling ball is not the falling ball. Now let me dig into this more carefully, because I do not want you to think I am just being a wise guy picking on mathematicians for sport. There is something genuinely deep going on here. Something that most people, even most scientists, do not think about carefully enough. When a mathematician works, what does he actually do? He starts with axioms. Axioms are the rules of the game. They are not proved. They are assumed. You just declare them to be true, and then you see what follows. In Euclidean geometry, for example, you start with things like a straight line can be drawn between any 2 points, and all right angles are equal. Fine. From those starting points, you can derive an enormous amount of geometry. The Pythagorean theorem, the formula for the area of a circle, all of it. But here is the thing. Those axioms are chosen. They are not discovered in nature. They are human inventions. And you can choose different axioms and get different mathematics. In the 19th century, mathematicians figured this out. They said, what if we change one of Euclid's axioms? What if we say that parallel lines can meet, and they got a completely different geometry, non-Euclidean geometry, perfectly self-consistent, perfectly logical, and for about 50 years everyone thought it was just a mathematical curiosity, a toy, an intellectual game. The man who started this was Nikolai Lobachevsky, a Russian mathematician. He said, what if through a given point you can draw more than one line parallel to a given line? And he worked out the consequences. Triangles whose angles add up to less than 180 degrees, spaces that curve like saddles, bizarre, counterintuitive, but logically perfect. Around the same time, Bernard Riemann went in the other direction. He said, what if there are no parallel lines at all? What if every pair of lines eventually meets? And he got yet another geometry. Triangles whose angles add up to more than 180 degrees. Spaces that curve like the surface of a sphere. Now both of these geometries are just as true as Euclid's, in the mathematical sense. They follow from their axioms with perfect logic. A mathematician has no basis for preferring one over another. They are all equally valid. Then Einstein came along and showed that the actual geometry of the universe is non-Euclidean. Space itself curves in the presence of mass and energy. Riemann's geometry, the one with positive curvature, turns out to describe the space-time around stars and planets. The mathematical game turned out to describe reality. But it did not have to. The mathematicians were not trying to describe reality. They were exploring logical possibilities. The fact that one of those possibilities matched the real world was a kind of miracle. Or maybe not a miracle, but at the very least, an astonishing coincidence that demands explanation. My colleague Eugene Wigner, a very fine physicist, wrote a famous paper about this. He called it the unreasonable effectiveness of mathematics in the natural sciences. And that word unreasonable is doing a lot of work in that title because it is unreasonable. There is no good reason why a game played with abstract symbols, chosen for their logical elegance, should turn out to describe the behavior of electrons and galaxies and everything in between. And yet it does, over and over again. Mathematics that was developed for purely abstract reasons turns out, decades or centuries later, to be exactly what physicists need to describe some new phenomenon. Group theory was developed in the 19th century as pure mathematics. Nobody was thinking about physics. They were thinking about symmetry and algebra, and then in the 20th century it turned out to be the key to understanding elementary particles. The patterns of particles, the way they interact, the conservation laws they obey, all of it maps onto group theory with breathtaking precision. Non-Euclidean geometry, as I just mentioned, developed as a mathematical curiosity, turned out to be the geometry of the actual universe. Complex numbers, numbers with a so-called imaginary part. Mathematicians played with these for centuries, and many people thought they were just a trick, a convenient fiction. Then quantum mechanics came along, and the wave function, the fundamental object of the theory, is a complex number, not as a convenience, not as an approximation. The universe apparently runs on complex numbers. How is that possible? How can mathematicians, sitting in their offices inventing abstract games, keep accidentally discovering the operating system of the universe? That is a mystery. A real honest-to-goodness mystery. And it is a mystery that the mathematicians themselves rarely address. They are too busy proving theorems. They do not stop to ask why their theorems keep turning out to be useful for describing nature. They just say, well, of course, mathematics is the language of the universe, and they go back to their proofs. But that is not an explanation. That is just restating the mystery in a more confident tone of voice. And here is where the physicist has something the mathematician does not. The physicist has a guide, a compass, something to tell him whether he is on the right track. And that compass is experiment, the real world. When a physicist writes down an equation, he is not asking whether it is logically consistent. He is asking whether it is true, whether it matches what happens when you actually go out and measure something. And that is a fundamentally different question. There is something else the physicist has. I call it seat-of-the-pants feeling. And when you know what you are talking about, when you know that these symbols represent forces and these represent masses and this here is inertia, then you can use common sense. You can use your intuition about how the world behaves. You can smell when something is wrong, even before you can prove it, because the physical world gives you clues that the mathematical world does not. If I write down an equation and the answer tells me that a ball should fall upward, I know something is wrong. I do not need to check my proof. I do not need a theorem. I just need to look out the window. The mathematician has no window. The mathematician has only the internal logic of the system. And internal logic by itself cannot tell you whether your starting assumptions connect to anything real. Let me give you an example, an important one. When I was working on quantum electrodynamics, I developed a method for doing calculations. You may have heard of Feynman diagrams, little pictures with lines and squiggles that represent particles interacting. Now, behind those diagrams is a mathematical technique called the path integral. The idea is very simple to state. If you want to know the probability that a particle gets from point A to point B, you consider every possible path the particle could take, every single one. Not just the straight line, not just the curved line, but every conceivable trajectory, including ones that go to the moon and back, ones that zigzag wildly, ones that make no sense at all. You assign a number to each path, a kind of weight, and then you add all those numbers up, and the sum tells you the probability. Now, when I first proposed this, the mathematicians were horrified, absolutely horrified. And I understand why. Because from a mathematical point of view, what I was doing was nonsense. You cannot just add up an infinite number of things, not without being very careful about what you mean by add up and what you mean by infinite. The mathematicians had spent decades developing rigorous theories of integration, careful definitions of what it means to sum over infinite collections, and my path integral did not fit into any of them. It was, from a mathematical standpoint, not well defined. There is no measure. That was their complaint. In mathematics, if you want to integrate over some space, you need a measure, a way of assigning sizes to subsets of that space. Norbert Wiener had developed a perfectly good measure for a related problem, Brownian motion, random walks. But Wiener's measure does not work for my path integral. The oscillating complex exponential, the thing that makes quantum mechanics quantum, refuses to be tamed by Wiener's approach. Let me explain why, because it is illuminating. In Brownian motion, the paths you are summing over are like a drunkard's walk. Each step is random, but the probabilities are always positive. You can assign a probability to each path, and those probabilities add up nicely. The mathematics works out. Wiener handled it beautifully. But in quantum mechanics, each path does not get a probability. It gets a complex number, a number with a real part and an imaginary part. And these complex numbers do not just add up, they interfere with each other. Some cancel out, others reinforce. The whole phenomenon of interference, which is the essence of quantum behavior, comes from this cancellation and reinforcement of complex amplitudes over different paths. And this interference makes the integral wildly oscillatory. It does not converge in any conventional mathematical sense. The mathematicians look at it and say, this does not meet our standards of rigor. This is not a well-defined mathematical object. You cannot just wave your hands and say you are summing over all paths. What does that even mean? Over what space? With what topology? What sigma algebra? What measure? And here is what I say back. I say I do not know. I do not know the rigorous mathematical foundations of the path integral. I know it works. I know how to use it. I know the rules for computing with it. And I know the answers I get agree with every experiment that has ever been done. Decades later, the mathematicians still have not found a fully rigorous measure for the Feynman path integral. Not for the general case. They have made progress, yes. They have handled special cases. The imaginary time version, where you replace the oscillating factor with a decaying one, that can be made rigorous using Wiener's methods. That is what the Feynman catch formula is about. But the real-time version, the one that actually describes quantum mechanics as it happens in the real world, that thing does not exist in the mathematicians' world. Not rigorously. Not fully. And here is the kicker. It works. The path integral gives answers. Concrete numerical answers. And those answers agree with experiment to an extraordinary degree of precision. When you use my methods to calculate, say, the magnetic moment of the electron, you get a number that matches the experimental measurement to about 10 decimal places, 1 part in 10 billion. That is like predicting the distance from New York to Los Angeles and being accurate to less than the thickness of a human hair. So the mathematicians say this is not rigorous, and the physicists say it agrees with experiment to 10 decimal places, and that right there is the entire difference between mathematics and physics in one sentence. The mathematician says, is it proven? The physicist says, does it work? These are not the same question. They are not even in the same neighborhood. And this is what I meant when I said to that room full of mathematicians, which ones are real? Because you can build a perfectly rigorous theory of 17-dimensional spaces and prove beautiful theorems about them, and the whole enterprise is mathematically impeccable. But if the universe has 3 dimensions of space and 1 of time, then your 17-dimensional theorems, true as they are, tell you nothing about reality. And that brings me to a point that I think deserves more attention than it usually gets. Mathematicians and physicists have different jobs, and we have gotten confused about that. Meanwhile, my path integral, sloppy and unrigorous as the mathematicians say it is, describes the behavior of every electron, every photon, every quark that has ever been measured. So who is right? The person with the airtight proof about something that does not exist, or the person with the messy method that describes what does? I think the answer is obvious. But it took me a long time to understand why it is not obvious to everybody. Let me tell you how a physicist actually works, so you can feel the difference. When I was working on quantum electrodynamics in the late 1940s, I had a problem. The calculations kept giving infinity, literally. You would set up the integral for, say, the self-energy of the electron, the energy the electron gets from interacting with its own electromagnetic field, and the answer would be infinity. Not a big number, not a very big number, infinity. Now, a mathematician confronted with this would say, your theory is inconsistent, an infinite answer is meaningless. You need to go back and fix your axioms. And that is perfectly reasonable from a mathematical standpoint, but I did not do that. Instead, I did something that would make a mathematician's hair stand on end. I subtracted one infinity from another infinity and got a finite answer. This is called renormalization, and it sounds insane. It sounds like cheating. You take an infinite quantity, you subtract another infinite quantity, and you claim the difference is some specific number. How can you do that? Well, you have to be very clever about how you do it. The key insight is that the infinities always appear in quantities that you can absorb into the measured values of physical parameters. The mass of the electron, the charge of the electron, things you do not calculate from the theory anyway, things you measure in the lab. So you say, fine, the bare mass is infinite and the correction is also infinite, but the difference, the physical mass that you actually observe, is whatever the experiment says it is. You build the measured values right into the theory, and the infinities cancel. Julian Schwinger worked this out independently in a very different and more mathematically rigorous way. Shinichiro Tomonaga did the same in Japan. And Freeman Dyson showed that all three approaches, mine, Schwinger's, and Tomonaga's, give the same answers. So we all got the Nobel Prize. But the important point is this: the mathematics at the deepest level was not rigorous. It could not be, because we were subtracting infinities. We were manipulating expressions that had no well-defined mathematical meaning, and yet the final answers, the predictions of the theory, matched experiment with extraordinary precision. That is the physicist's approach. You do not wait for the mathematicians to hand you a rigorous foundation. You press forward. You use whatever methods work. You check your answers against experiment, and if the answers match, you have learned something about nature, even if the mathematics underneath is not fully understood. Here is another way to see the difference. I have said this before, and I will say it again because it is important. The mathematician says, is it proven? The physicist says, does it work? The mathematician's job is to explore the landscape of logical possibility. All of it, every corner. He has no obligation to check whether any of it corresponds to the physical world. He is a map maker who draws maps of every conceivable country, including ones that do not exist. And that is fine, that is valuable, because sometimes we physicists need a map of a country we did not know existed, and we are glad the mathematician drew it ahead of time. But the physicist's job is different. The physicist's job is to figure out which map matches the actual territory, and that means we have a tool the mathematician does not have: nature itself. We can go outside and check, we can run experiments, we can measure things, and measurement is the ultimate authority. Not proof, not logic, not beauty. Measurement. This is why I always told my students, it does not matter how beautiful your theory is. It does not matter how smart you are. It does not matter how elegant your equations are. If your theory disagrees with experiment, it is wrong. Period. And that, I think, is what made the mathematicians uncomfortable when I asked my question, because they have no equivalent statement. They cannot say, if your theorem disagrees with experiment, it is wrong, because their theorems are not about experiments. Their theorems are about abstract structures that may or may not have anything to do with the real world. And there is no procedure, no test, no experiment that can tell them whether their abstract structures are real in the sense that a physicist means. Now, I want to be fair here. I am not saying mathematics is useless. Far from it. Mathematics is essential to physics. Without it, we could not do what we do. The laws of nature are written in mathematical form, and we need mathematical tools to extract their consequences. But here is the critical point that most people miss. The mathematics is a tool, not the thing itself. The equation F equals m times a is not gravity. It is a description of gravity. A very good description, as it turns out. But the description is not the reality. The map is not the territory. And when you keep that distinction clear, you start to see things differently. You start to ask different questions. You stop asking, is this mathematically elegant? And you start asking, does this match what actually happens? And those two questions lead you in very different directions. Let me give you another example of how this works in practice. When you learn physics in school, you learn about Newton's laws. Force equals mass times acceleration. Every action has an equal and opposite reaction. These laws can be derived from a beautiful mathematical framework called Lagrangian mechanics, which in turn can be derived from an even more abstract framework called Hamiltonian mechanics. And the mathematicians love Hamiltonian mechanics. It is gorgeous, it has symmetry, it has structure. It has a deep connection to something called symplectic geometry, which is a whole field of mathematics unto itself. But here's the dirty secret. When you actually go into a lab and measure things, you do not use Hamiltonian mechanics. You use whatever works. Sometimes that is Newtonian mechanics. Sometimes that is Lagrangian mechanics. Sometimes that is my path integral. Sometimes that is a computer simulation with no elegant mathematical structure whatsoever. The physicist uses the tool that gets the job done. He does not care which tool is more fundamental. In some abstract mathematical sense, he cares which tool gives the right answer. And this drives mathematicians crazy, because to them it feels sloppy, it feels unprincipled. How can you use a method that is not rigorous? How can you trust a calculation that is not proven? How can you build a theory on a foundation that, mathematically speaking, does not exist? I had a friend, a very good mathematician, who once said to me, "Dick, your path integral is not mathematics. It is black magic." And I said, "Sure, but it is black magic that gets the right answer. Can your rigorous methods do better?" And he had to admit that they could not for the problems I was solving. Not even close. And my answer is always the same. I trust it because it works. I trust it because when I use it to predict what will happen in an experiment, the experiment confirms the prediction. That is the only kind of trust that matters in physics. Now let me push this even further, because there is an even deeper issue lurking behind all of this. Suppose for a moment that the mathematicians are right. Suppose that the real foundation of physics is mathematics, that nature is, at bottom, a mathematical structure, and we are just discovering the properties of that structure. This is a very old idea. Plato believed something like it. He thought that the physical world was a shadow of a more perfect world of abstract forms, and many modern physicists flirt with this idea too, but I want you to think about what this really means. If nature is fundamentally mathematical, then which mathematics is it? Because the mathematicians have shown us that there are infinitely many possible mathematical systems, infinitely many geometries, infinitely many algebras, infinitely many topologies. They are all logically consistent. They are all true in the mathematical sense. But the universe appears to use only a very small subset of them. Why? Why Euclidean geometry and not some other geometry? Well, actually, it is not quite Euclidean. It is Riemannian. Why Riemannian and not something else? Why complex numbers instead of some other number system? Why the particular symmetry groups that appear in particle physics and not the thousands of other groups the mathematicians have classified? These are physics questions, not mathematics questions. And they cannot be answered by mathematical proof. They can only be answered by experiment, by going out and looking at nature and seeing what nature actually chose, because nature did choose. Out of all the possible mathematical structures, nature is doing one particular thing, and we are trying to figure out what it is. And the mathematician, for all his brilliance, cannot help us with that part. He can lay out the menu, but he cannot tell us what nature ordered. This is what I mean when I say that physics is to mathematics as sex is to, well, something solitary. In physics there is another party involved. There is nature, and nature has opinions. Nature pushes back. Nature surprises you. You think you understand what is going on, and then you do an experiment, and nature says, "No, you are wrong," and you have to go back and think again. The mathematician never has this experience. The mathematician is always right because his conclusions follow logically from his premises. But being always right about an abstract game is not the same as understanding the physical world. And this, I think, is the deepest lesson. The power of physics does not come from mathematical rigor. It comes from contact with reality. It comes from the fact that we are willing to be wrong, that we are willing to have our most beautiful ideas destroyed by an ugly experimental fact. The mathematician never risks this. His theorems are safe. They live in a protected world where experiment cannot touch them. But the physicist walks out into the open, exposes his ideas to the harsh light of experiment, and sees which ones survive. And the ideas that survive that process are not just mathematically true, they are true about the actual universe. And that is a much more impressive achievement. Now I want to come back to that room full of mathematicians, because there is one more thing about this encounter that I think is important. After I asked my question, after the silence, one of the mathematicians said something very interesting. He said, "But Professor Feynman, when we develop mathematics that later turns out to describe physics, Isn't that evidence that mathematics is more than just a game? Isn't it evidence that mathematical truth and physical truth are connected in some deep way? And I had to admit that is a fair point. It is the Wigner puzzle, the unreasonable effectiveness. Why does pure mathematics keep predicting physics? Why did non-Euclidean geometry, developed as a logical curiosity, turn out to describe the actual shape of space? Why did group theory, developed as abstract algebra, turn out to classify elementary particles? Why do complex numbers, which have no obvious physical meaning, sit at the very heart of quantum mechanics? These are real questions, and I do not have good answers for them. Nobody does. What I will say is this: the fact that mathematics is unreasonably effective does not mean that mathematics is physics. It means there is a deep connection between the two that we do not understand, and pretending we understand it by simply declaring that nature is mathematical does not help. It just sweeps the mystery under the rug. Let me give you one more example because it really drives the point home. There is a mathematical object called the Lie group, SU3. It is an abstract symmetry group. Mathematicians studied it because it has nice properties. It is compact. It is simple. It fits into a beautiful classification scheme that the mathematician Gilles Cartan worked out in the 1890s. Pure mathematics, no physics in sight. Then, in the 1960s, Murray Gell-Mann and others noticed that the zoo of elementary particles, the protons and neutrons and pions and kaons and all the rest, organized themselves perfectly into the representations of SU3. The patterns matched exactly, and not just approximately. The symmetry predicted new particles that had not been seen yet. Gell-Mann predicted a particle he called the omega minus, based entirely on the mathematical pattern. It had to exist if SU3 was the right symmetry, and when experimentalists went looking for it, there it was, with exactly the properties the mathematics demanded. Now that is extraordinary. A symmetry group studied for its abstract beauty in the 1890s turns out to classify the fundamental building blocks of matter in the 1960s. How? Why? What is the connection between the mathematician's aesthetic sense and the structure of the atomic nucleus? I do not know. Wigner did not know. Nobody knows. And I am suspicious of anyone who claims to know. But I can tell you what the answer is not. The answer is not that nature is mathematics. The answer is not that if you do enough math you will discover physics. Because for every mathematical structure that turns out to describe nature, there are thousands that do not. For every SU3 that works, there are endless other groups that do not correspond to anything physical. The hit rate is not 100%. It is actually very low. It just seems high because we only notice the successes. What I suspect, though I cannot prove it, is something like this. The reason mathematics works so well in physics is not that nature is inherently mathematical. It is that mathematics captures patterns, and nature is full of patterns. Wherever there is symmetry, wherever there is regularity, wherever there is repetition, mathematics can describe it. And nature happens to be saturated with symmetry and regularity, at least in the domains we have been able to explore. But that is a statement about nature, not about mathematics. Mathematics is the language we use to describe the patterns we find. It is a very good language for that purpose, but the patterns are nature's, not ours. Think of it this way. Suppose you had a language that was very good at describing shapes, circles, squares, triangles, spirals, and suppose you discovered that the natural world is full of shapes. Honeycombs are hexagonal, planets are roughly spherical, galaxies form spirals. You might be tempted to say that the universe is fundamentally linguistic, that the universe is made of words. But that would be silly. The universe is made of stuff, physical stuff that happens to form shapes. The shapes are real. The language is just how you talk about them. Mathematics is like that. It is a language for talking about patterns, a spectacularly powerful language, because it can describe patterns with extraordinary precision. But the patterns are in nature. The language is in our heads. And this is why the physicist beats the mathematician in the end. Not because the physicist is smarter. Often the mathematician is smarter in the sense of being a more powerful abstract thinker. But the physicist has something the mathematician does not, a willingness to listen to nature, to let nature be the teacher, to let experiment be the final word. And nature, as it turns out, has far more imagination than any mathematician. I want to say something about this idea of listening to nature, because I think it is deeply misunderstood. People think physics is about imposing order on the world. writing down equations and declaring that the world obeys them. But that is exactly backwards. Physics is about submitting to the world. It is about admitting that you, with your big brain and your clever equations, do not get to decide how things work. Nature decides, and your job is to shut up and pay attention. This is why the greatest discoveries in physics have always been surprises. Nobody expected quantum mechanics. The idea that a particle does not have a definite position until you measure it, that it exists in a kind of blur of possibilities, that the act of observation changes the thing being observed. No mathematician would have invented that. It violates common sense. It violates classical logic. It seems, from a purely mathematical standpoint, unnecessary. Why should the universe work this way? There is no mathematical reason. There is no logical reason. Nature insists upon it. Or take the speed of light. There is no mathematical reason why there should be an ultimate speed limit. You can write down perfectly consistent mathematical systems where there is no speed limit. You can write down systems where information travels instantaneously. The mathematics works fine, but the universe chose a speed limit, roughly 186,000 miles per second, and every consequence that follows from that fact, time dilation, length contraction, the equivalence of mass and energy, all of those are physics, not mathematics. They are things that nature forced upon us by refusing to work any other way. You know, there is a phrase I am fond of. I once said that if all mathematics disappeared today, physics would be set back by exactly 1 week. Now that is an exaggeration. I was being deliberately provocative, but the spirit of the remark is true. The ideas of physics, the insights about how nature works, are not mathematical ideas, they are physical ideas. You can express them in mathematical language, and you should, because that is the most precise way to express them. But the ideas themselves are about the world, not about symbols on a page. And the wonderful riposte to that, which I have to admit is very clever, came from a mathematician who said yes, but it would be the week in which God created the world. Meaning, of course, that the mathematics underlying physics is so deep and so fundamental that it amounts to the architecture of reality itself. And that is a beautiful thought. But it is still a metaphor. It is still a way of expressing our awe at the connection between mathematics and nature, not an explanation of that connection. So what did I learn from destroying that room full of mathematicians? I learned something I already knew, but that I understood better for having tested it. Mathematics is powerful. Mathematics is beautiful. Mathematics is essential. But mathematics is not physics. Mathematics tells you what is logically possible. Physics tells you what actually happens. And those are two very different things. The mathematician can prove that a certain kind of universe is logically consistent. The physicist can show you which universe you actually live in. The mathematician can tell you that a ball could roll uphill if you rearrange the forces just so. The physicist can drop the ball and show you which way it goes. And here is the final thing I want to leave you with. This distinction between mathematical truth and physical truth is not a minor technical point. It is not a quibble between academic departments. It is one of the most important ideas in all of science. Because if you confuse the two, if you mistake the map for the territory, you will spend your life proving theorems about imaginary worlds, while the real world sits outside your window, waiting to be explored. The real world. That is what physics is about. Not the elegant world of mathematical abstraction, but the messy, surprising, endlessly fascinating world that you can touch and measure and break and reassemble. The world where things actually happen, where particles collide, where stars explode, where light bends around massive objects, where electrons do things that no amount of pure logic could have predicted. I have spent my whole life studying this world, and the thing that strikes me again and again is how much more interesting it is than anything we could have invented. No mathematician sitting alone with a blank page could have dreamed up quantum mechanics. It is too strange, too counterintuitive, too different from any mathematical structure that existed before physicists were forced by experimental evidence to invent it. And this is where I must come back to something that really bugs me. There is a tendency among theoretical physicists, especially the young ones, to become too mathematical, to lose contact with nature, to start believing that if an equation is beautiful enough, it must be right. And I want to warn you against that tendency. I have seen it happen many times. A brilliant young person comes up with a beautiful mathematical framework. Elegant, symmetric, gorgeous. They fall in love with it. They write papers about it. Other theorists cite those papers and write more papers. A whole community builds up around this beautiful mathematical structure, and nobody checks whether it has anything to do with the real world. Nobody does the hard, unglamorous work of comparing the predictions to actual measurements, because the mathematics is so beautiful that it feels like it must be right. And then 10 or 20 years later, the experiments come in, and the beautiful theory is wrong. Not because the mathematics is wrong. The mathematics is perfect. The theorems are all correct. But the axioms, the starting assumptions, do not match reality. The map is gorgeous, but it is a map of a country that does not exist. I always told my students, look at the data. First, last, and always, look at the data. Do not fall in love with your equations. Do not trust beauty over evidence. Do not let mathematical elegance seduce you into ignoring what nature is actually telling you, because nature is the most creative storyteller there is. The plot twists are real, and no amount of mathematical proof can substitute for the experience of finding out what actually happens when you drop a ball, spin an electron, or send a photon through two slits. Let me tell you one more little thing that illustrates the difference. When the mathematicians work on a problem, they can take their time. There is no rush. A conjecture can sit open for centuries. Fermat's last theorem was proposed in 1637 and not proved until 1995. That is over 350 years. And the mathematicians were perfectly happy to wait, because mathematical truth does not expire. It is the same today as it was in the 17th century, but the physicist cannot wait. The physicist has experiments running right now, data pouring in right now, questions that need answers right now, and so the physicist develops a different relationship with mathematics. The physicist uses mathematics the way a carpenter uses a hammer. You pick it up when you need it. You put it down when the job is done. You do not worship the hammer. You do not build a shrine to it. You use it to build a house, and the house is what matters. That is how I have always felt about mathematics. It is the most powerful tool we have, and I am grateful to the mathematicians for building such fine tools. But the tool is not the thing. The thing is the understanding of nature. The thing is the explanation of why the world works the way it does. And that understanding comes from experiment, from observation, from patient, careful engagement with the physical world. Not from proofs, not from axioms, not from the manipulation of abstract symbols. Nature is not just a math problem to be solved. Nature is a partner to be danced with. And the dance is messy and unpredictable and full of wrong steps and do-overs. But it is real, and that makes it infinitely more valuable than the most perfect proof in the most beautiful theorem in the most elegant mathematical system ever devised. So if you are sitting in a room full of mathematicians, and they are telling you about the beauty and certainty and perfection of their subject, just ask them one question. Ask them, which of your beautiful truths is actually true? Not logically true, not abstractly true. True about the universe you live in, true in the way that a falling apple is true. And then enjoy the silence. That is the question I want you to sit with tonight. When you see a mathematical equation describing something in nature, ask yourself, is the equation the truth? Or is it the best story we have been able to tell about the truth? And what would it mean if there is a difference?